From the dawn of civilization, it has captivated humanity, a symbol of power, wealth, and enduring beauty. Its very name evokes images of ancient empires, hidden treasures, and the relentless pursuit of ultimate value. But what truly lies behind the shimmering allure of gold? How does this precious metal, born deep within the Earth's crust, transform from raw, unyielding rock into the pure, gleaming bars that underpin global economies and adorn our lives? Imagine a world hidden from plain sight, a realm of intense heat, precise chemistry, and cutting-edge technology. This is not a mythical kingdom, but a modern marvel of engineering and human ingenuity, the gold refining factory. It is here, within these fortified walls, that the raw essence of the earth undergoes an alchemical transformation, a journey from crude ore to an almost impossibly pure state. This isn't just about melting metal, it's a meticulous dance between science and industry, a testament to humanity's drive to extract and perfect nature's most coveted element. Step with us now, beyond the guarded gates, into a world where every gram matters, where the faintest impurity is a challenge to be overcome, and where the promise of 24-karat perfection drives every single process. This is the hidden world behind everyday products, the unseen journey of the very gold that might be in your jewelry, your electronics, or even the reserves of nations. Prepare to uncover the secrets, the drama, and the sheer industrial might required to bring forth pure gold. It's a story of discovery, satisfaction, and an industrial mystery unfolding before your eyes, revealing the intricate ballet of turning rock into unparalleled brilliance. Gold's journey from the Earth's embrace to a gleaming bar is far more intricate and fascinating than most imagine. It's a story steeped in history, driven by innovation, and punctuated by mind-blowing details. Consider, for instance, that nearly all the gold on Earth is believed to have arrived here from meteorite impacts billions of years ago, scattering across the planet during its formation. This cosmic origin story imbues every speck of gold with an almost extraterrestrial mystique. The sheer rarity of gold is staggering. If all the gold ever mined in human history were melted down, it would form a single cube roughly 22 meters on each side. That's enough to fill just 3 Olympic-sized swimming pools. Yet, its value and impact on civilization are immeasurable, extending far beyond its physical volume. Historically, the pursuit of gold has shaped empires, ignited wars, and spurred some of humanity's greatest migrations. The California gold rush of 1849, for example, wasn't just about individual prospectors panning for nuggets. It was a catalyst for massive technological advancements in mining and metallurgy, transforming entire regions and economies. Early refining methods were crude, often involving mercury to amalgamate gold, a process that was both inefficient and incredibly toxic, leaving a devastating environmental legacy. The shift from these dangerous, rudimentary techniques to modern, sophisticated refining processes represents a monumental leap in industrial chemistry, environmental responsibility, and worker safety. Today, the purity standards are astonishingly high, often reaching 99.99% or even 99.999% pure gold, a level of perfection unimaginable to ancient alchemists who toiled for centuries in vain attempts to create gold. But what makes gold so special, beyond its scarcity and beauty? Its unique properties are key to its enduring value and widespread utility. Gold is incredibly malleable and ductile. A single ounce can be drawn into a wire 5 miles long or hammered into a sheet so thin it's transparent, only a few atoms thick. This extreme workability makes it invaluable not just for intricate jewelry designs, but for critical industrial applications where other metals simply fail. Think about the micro-thin gold coatings in astronaut visors, reflecting harmful solar radiation and protecting delicate eyes, or the tiny gold wires connecting components in your smartphone, ensuring reliable electrical conductivity in a non-corrosive environment, vital for long-term device performance. Its inertness, its remarkable resistance to corrosion and tarnish, is another marvel. Unlike most metals, gold doesn't react with oxygen, moisture, or most acids, making it eternally lustrous and a perfect long-term store of value, a quality that has been recognized across millennia and cultures. The global gold market is a complex web of mining, refining, trading, and investment, operating 24 hours a day across continents. Did you know that the largest gold reserves in the world are held by the United States, with over 8,133 metric tons stored primarily at Fort Knox? This vast quantity underscores gold's role as a bedrock of national economies and a critical component of global financial stability. Beyond central banks, individual investment in gold has soared, driven by its reputation as a safe haven asset during economic uncertainty and geopolitical instability. The intricate logistics of moving, securing, and auditing such immense wealth are a marvel in themselves, involving high-security transport, state-of-the-art vaults, and a global network of trusted institutions. The sheer volume of gold traded daily on exchanges like the London Bullion Market Association, LBMA, is staggering, with hundreds of tons changing hands virtually, reflecting its constant demand. Modern innovations in gold refining are constantly pushing the boundaries of efficiency, purity, and environmental responsibility. New methods aim to reduce the use of harsh chemicals, minimize energy consumption, and recover even the smallest traces of gold from increasingly complex ores and secondary sources. For instance, bioleaching, a process that uses specialized microorganisms to selectively dissolve and extract metals from ore, is an emerging technology that promises a greener, less energy-intensive future for gold mining and refining. This contrasts sharply with historical methods that often left devastating environmental legacies, polluting waterways and landscapes with toxic byproducts. The engineering challenges in designing and operating a modern gold refinery are immense. It's not just about applying chemical principles, it's about managing extreme temperatures, handling highly corrosive and sometimes toxic substances, and ensuring the absolute safety of both highly valuable materials and the skilled personnel involved in every step. Consider the concept of invisible gold. Much of the world's gold isn't in gleaming bars or intricate jewelry. It's microscopically embedded in the electronic waste of discarded devices. A ton of old mobile phones, for example, can contain more gold than a ton of gold ore from a typical mine. This startling fact has spurred an entirely new industry, urban mining, where precious metals are recovered from e-waste. This circular economy approach highlights gold's enduring value and the ingenuity required to reclaim it from increasingly diverse and complex sources. The precision involved in extracting these microscopic quantities is astounding, often requiring highly specialized chemical processes to separate gold from a complex matrix of other metals, plastics, and ceramics, a testament to the economic viability of even minute recoveries. The purity of gold is measured in carats, with 24K representing 99.9% pure gold. But achieving this level of purity from raw ore, which might contain only a few grams of gold per ton, is a monumental task. It involves a series of crushing, grinding, chemical leaching, and electrolytic processes, each designed to progressively remove impurities with increasing specificity. The difference between 22K gold, often used in jewelry for its enhanced durability due to alloying, and 24K gold, prized for its absolute purity in investment and industrial applications, is significant in the refining world. While 22K contains 91.6% gold, the remaining percentage is typically made up of other metals like copper or silver, added to enhance strength and alter color. Refiners must meticulously separate these alloying elements to achieve the ultimate 24K standard, a process demanding exceptional control and analytical capability. Even the smallest details in the refining process can have a profound impact on the final product's purity and efficiency. The precise temperature of a solution, the exact concentration of a chemical reagent, the duration and intensity of an electrical current, all are meticulously controlled and continuously monitored. This level of precision is why gold refining is often compared to a high-stakes scientific experiment conducted on an industrial scale, where deviations of even a fraction of a percent can affect the outcome. The global relevance of gold extends beyond its monetary value. It's a critical component in advanced medical devices like pacemakers and dental fillings, aerospace technology where its conductivity and corrosion resistance are vital, and even catalytic converters in cars, where it aids in reducing harmful emissions. Its unique combination of properties makes it irreplaceable in many high-tech applications, underscoring its multifaceted importance in the modern world and its continuous demand across diverse sectors. The journey of gold, from the moment it is extracted from the earth to its final form as a pure 24K bar, is a testament to meticulous engineering, sophisticated chemistry, and unwavering quality control. It begins far from the refinery, in mines where gold-bearing ore is unearthed. This raw material, often a mixture of gold, silver, copper, and various other minerals, arrives at the refining facility in diverse forms. D'or bars, a semi-pure alloy of gold and silver, typically 70 to 90% pure, scrap metal from industrial processes, or even complex electronic waste containing minute but valuable quantities of gold. The factory's first task is to meticulously sort, categorize, and prepare these varied inputs, as each requires a slightly different initial approach. Upon arrival, all materials are subjected to rigorous weighing and sampling with extreme precision. D'or bars are typically melted down and cast into smaller, more uniform anodes for subsequent electrolytic refining. Scrap materials undergo initial shredding, crushing, or granulation to increase their surface area, making them more amenable to chemical processing. The goal at this preliminary stage is to homogenize the input as much as possible, ensuring consistent processing downstream and maximizing recovery rates. Throughout this initial handling, stringent safety protocols are paramount, with strict handling procedures for all materials, especially those that might contain hazardous components from e-waste or industrial scrap. Personnel wear specialized protective gear, and ventilation systems are robust to manage any fumes or dust. The primary method for achieving the highest purity gold, often 99.99% or 99.999%, is the Wohlwill process, an advanced electrolytic refining technique. This process begins by casting the impure gold, anodes, into specific, uniform shapes. These anodes are then carefully submerged in an electrolyte solution, typically chlororic acid, alongside thin sheets of pure gold, which act as cathodes. When a precisely controlled electric current is passed through the solution, the impure gold anode slowly dissolves. Gold ions, carrying a positive charge, migrate through the electrolyte and are attracted to the negatively charged pure gold cathode sheets, where they deposit as pure gold. Impurities like silver, platinum, and palladium, depending on their electrochemical potential, either settle as a valuable sludge at the bottom of the electrolytic cell, known as anode slime, or remain dissolved in the solution, allowing for their separate recovery. This controlled dissolution and deposition allow for an astonishingly effective separation of gold from other metals, achieving exceptional purity. Another critical refining method, especially for lower-grade gold or for pre-refining to reduce the impurity load before electrolysis, is the Miller process. This involves bubbling chlorine gas through molten impure gold, typically heated to around 1100 to 1200 degrees Celsius in a specialized furnace. Chlorine reacts preferentially with base metals like copper, lead, and zinc, as well as silver, forming their respective chlorides. These chlorides, being less dense than molten gold, either volatilize and are captured by exhaust systems or form a distinct slag layer on the surface of the molten gold, which can be skimmed off. This process is significantly faster than electrolytic refining but typically yields gold of around 99.5% purity, often requiring subsequent Wohlwill refining for the ultimate 24K standard. The intense heat required for melting and the careful handling of corrosive and toxic chlorine gas demand robust industrial furnaces, specialized refractory materials, and advanced ventilation and gas scrubbing systems to ensure environmental compliance and worker safety. Throughout these complex processes, automation plays a crucial role in enhancing efficiency, precision, and safety. Robotic arms are employed to handle heavy anodes and cathodes, transferring them between cells with unwavering precision, minimizing human exposure to hazardous environments and high temperatures. Automated systems continuously monitor critical parameters such as electrolyte concentrations, solution temperature, current density, and pH levels, making real-time adjustments to optimize efficiency and purity. Conveyor systems seamlessly transport materials between different stages, from initial melting and casting to the electrolytic cells and final pouring, ensuring a continuous and streamlined flow of production. This integration of robotics and automated control systems allows for consistent quality and high throughput. Quality control is not merely a final check. It is an ongoing, rigorous process embedded at every single stage of refining. Samples are meticulously taken at every critical juncture, from incoming materials to the electrolyte solution, from the anode slime to the deposited gold on the cathodes, and finally from the finished bars. These samples are analyzed using sophisticated analytical techniques such as inductively coupled plasma, ICP, spectrometry, X-ray fluorescence, XRF, and atomic absorption spectroscopy to detect and quantify even trace amounts of impurities down to parts per million or even parts per billion. This continuous, multi-point monitoring ensures that the refining process is performing optimally, that any deviations are immediately addressed, and that the final product consistently meets the stringent 24K purity standard, which often means 99.99% or even 99.999% pure gold, verified by independent assays. Once the gold reaches the desired purity on the cathodes, it is carefully removed. These pure gold sheets are then melted in high-frequency induction furnaces. These furnaces provide rapid, clean melting, minimizing any potential contamination from fuel sources and allowing for precise temperature control. The molten gold is then meticulously poured into preheated molds, typically made of high-purity graphite, to form the iconic gold bars. The size and weight of these bars vary significantly, from small investment ingots weighing a few grams to the standard 400-ounce, approximately 12.4 kilograms, good delivery bars used in international trade and held by central banks. Each bar is then precisely weighed, stamped with its exact weight, its purity, e.g., 999.9 or 999.99, a unique serial number for traceability, and a refiner's hallmark, which serves as a guarantee of its authenticity and quality, recognized globally. Finally, the finished gold bars undergo a final visual inspection, precise weighing, and secure packaging. Logistics for these incredibly valuable assets are among the most stringent in the world, involving highly secure transportation, often armored vehicles, specialized vaults, and meticulously planned routes, to move them to central banks, financial institutions, or secure storage facilities around the globe. Every movement is tracked and audited. Safety is paramount at every step, not just for the precious metal, but for the personnel involved. Gold refining factories are equipped with advanced ventilation systems, comprehensive emergency response protocols, fire suppression systems, and multi-layered access controls, ensuring a secure and controlled environment for this incredibly valuable and precise operation. What an incredible journey, from raw rock to the unparalleled brilliance of a 24K gold bar. We've peeled back the layers of an industry that is both ancient and cutting edge, revealing the intricate dance of chemistry, engineering, and human ingenuity that brings this precious metal to life. The sheer precision, the historical significance, and the mind-blowing technology involved in transforming crude ore into pure gold are truly astounding. It's a testament to human innovation and our relentless pursuit of perfection. But the world of industrial transformation is vast and full of even more hidden wonders. Have you ever stopped to think about the sheer scale of agriculture and food processing? Imagine a factory that doesn't just handle precious metals, but an organic raw material that feeds millions. How do factories manage to process enormous quantities of perishable crops, day in and day out, ensuring efficiency, minimizing waste, and maintaining quality on an unimaginable scale? It's a logistical and engineering challenge unlike any other. If you were captivated by the meticulous processes of gold refining, you won't want to miss our next deep dive. Click on the video that just appeared on your screen to go inside the factory. How factories handle 50 million cassava tubers every day. It's a fascinating look at another incredible feat of industrial logistics and processing, revealing the secrets behind feeding a global population. Don't forget to subscribe to our channel for more exclusive behind-the-scenes access to the hidden worlds of manufacturing, and hit the notification bell so you never miss an episode. Tell us in the comments below, what was the most surprising fact you learned about gold refining today? Was it the cosmic origin of gold, the intricate Wohlwill process, or the sheer rarity of all the gold ever mined? We love hearing your thoughts and engaging with our curious community.